Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at minor losses in pipe flow. In the previous video, we have discovered that there are two types of losses inside a pipe flow. First is called major losses, which is because of the friction inside the pipe. So the longer the pipe, the major losses will be higher. And then there's a second type of loss which is called minor losses. And minor losses is dependent on fittings that is inside the piping systems. And it is represented mathematically as HL equal to kV square over 2G. And if I label this, so HL is the minor loss, K is what we call loss coefficient, V is velocity, and as usual, G is gravity. Now remember that for the equation of major losses, the equation is HL equal to FL over D V square over 2G. Now this is the equation for major loss. So for major loss, you have this F, which is called the friction factor. But for minor loss, you have K, which is loss coefficient. Now the value of K is usually given in a table. Let me show you what this table looks like. Right, so this is what the loss coefficient table looks like. Okay, you can find this in your textbook, or if you Google loss coefficient, you will find this table. So nominal loss coefficient, or K. Now let's see. If a system has globe valve in it, let's say you have a pipe here, and then this meets a globe valve. Now, because the flow has to go through a valve, for instance, then there will be some losses occur inside that valve. For example, if you have a flow that goes through an entrance, something like this, okay, you may have a flow goes like that, and you may have some turbulent flow here, or you may have some vortex here. This is the source of losses. And these losses is represented as K. Now, as you can see in this table here, for valve, for instance, there are a few diameters of pipe that you need to consider. These are only a few diameters that we are going to consider in this lesson. Of course, when you graduate and you work in the real world, this table gets a lot bigger with each value of K assigned for each diameter of the pipe. And it depends on the fittings as well, whether the valve is screwed or if it's flanged. Now, a flange connection looks something like this. Okay, let's say you have this pipe and you need to connect this pipe to a valve, for instance. And a flange connection will have flange here, and this is connected to the valve through another flange, and this is your valve, for example. Okay, and this is usually bolted with many screws. And this is what we call a flange connection. For screwed connection, then the pipe is simply screwed into the valve. Now, if the flow goes through a bend, okay, this is a written bend, and then you have T or T-line, standard elbow. Now, I believe that this is very common if we do piping in our house, for example. Okay, and we also have long sweep elbow. And if you imagine, if standard elbow looks like this, okay, and a long sweep elbow might look something like this, right? Now, between this A and B, which one do you think will have greater losses? Of course, it's going to be A, because the flow has to turn a lot. That is why between standard elbow and long sweep elbow, if you notice, let's take an example of 10 centimeter pipe, right? So for standard elbow, K is 0.64. And for long sweep elbow, K is only 0.23. And if I write the equation again, HL is K V square over 2G. So the higher the K, the higher your minor losses. And let's see what else we have here. We have here square edge entrance. K value is 0.5. Re-entrant entrance, this is 0.8. Well around the entrance, 0.03. And pipe exit is something that you will see very often. The K value is 1. And then of course you have sudden contraction, orifice plate, sudden enlargement, and also general contraction. So I think in order to familiarize yourself with minor losses, let's do an example. So let's get back to our notes and let's do an example. Now let's say that we have a piping system that is supposed to deliver water from this tank to this tank. And the piping system looks something like this. First of all, you have a globe valve here. And then it goes through an elbow. And this pipe goes down. And we will have another elbow here. And let's say that the water level is here. And the difference between these water levels is H. Okay, and this is a 20-meter pipe. This is a 10-meter pipe. And this is also a 20-meter pipe. So it's not exactly to scale, but I hope you can understand it. And these fittings here is screwed elbows. And this is the same here as well. And what we have here is screwed globe valve. And this valve is fully open. And the diameter of this pipe is 100 millimeters. So all the pipes that is used in this problem has a diameter of 100 millimeter. And the material is wrought iron. Okay, so material is wrought iron. And also what is given to you in this problem is the flow rate, which is Q, equal to 0.04 meter cube per second. And finally, the question is asking you to find what is the difference in elevation between these two tanks. It means that the question is asking for the value of H. Okay, so now, how do we solve this problem? Alright, but before that, let me make it clear to you that this is the water. Okay, and this is another tank. And we're going to label this as point 1. And this is point 2. So the first thing that we need to do is that we need to relate point 1 and point 2 using energy equation. Okay, and do you still remember what energy equation looks like? Right, so energy equation is P1 over rho g plus V1 square over 2g plus Z1 equal to P2 plus rho g plus V2 square over 2g plus Z2 plus losses. And if you remember, if you have turbine in the system, this is plus HT, and if you have pump in the system, this is HP, right? But obviously we do not have pump and turbine, so I'm going to cancel these two out. And I think it's going to be quite simple to solve this energy equation because P1 and P2 is exposed to atmosphere. So P1 minus P2 will be 0. And also V1 and V2 can also be neglected because V1 and V2 is moving in this direction. And it's going to be small enough compared to the velocity of the flow, for example. Okay, so I'm going to cancel this out as well. And you are left with Z1 minus Z2 equal to HL. And Z1 minus Z2 is actually H. Okay, so H is actually HL. And remember that we are actually looking for the value of H. So it means that we are actually looking for the losses inside the piping system. Now let's see if we can find these losses, right? We know that HL has two components, which is major component and minor component. So this is major and minor. That means the total losses will be major losses plus minor losses. Let me write it here. So the total losses for this piping system is HL major plus HL minor. Let's write the equation for HL major. This is F L over D V square over 2G plus K V square over 2G, right? And HL is actually equal to H. So I'm going to rewrite this equation again. So H is equal to K V square over 2G plus FL over D V square over 2G. Now, this is quite straightforward because we only have a pipe, even though we have 3 pipes, right? But these 3 pipes, all of them has 100 millimeter diameter. And therefore, we only need to find this once. And then we're going to add the length of the pipe, that is 20 meter plus 10 meter plus 20 meter. And we're going to add it together inside this L. So that should be quite simple. But now we are looking for minor losses and we need to know what is the K. Now, because this system has many fittings, okay, let me show you. What you have here is the entrance flow. That is one value of K. And then you have this screwed globe valve that is 2 Ks. And then you have 2 elbows. So 3 and 4. So 3 and 4 Ks now. And you have exit flow. So you need to find 5 value of Ks and combine them together to complete this equation. Right? So let me write this for you. First, you're going to have K at entrance plus, and then you have K at the valve, K at the globe valve, and then you have the K of the elbows. So this is elbow plus K elbow because we have 2 elbows. And finally, you have K exit. And this is times V square over 2G plus FL over D V square over 2G. Now, it is up to you which one you want to find first, whether you want to find minor losses first or you want to find major losses first. But for now, let's try to solve this equation first. So later, we can focus on using the table in order to find these values. Okay, so first we need F. When we need F, we need Reynolds number and also we need the relative roughness. Reynolds number is equal to velocity times diameter divided by kinematic viscosity. So what we need now is V, and to find velocity is quite simple because we already have the flow rate and we also know the diameter. And flow rate is equal to velocity times area. Let's do this here. Q is equal to velocity times area. We are looking for velocity. This is Q divided by area. Q is 0.04 and area is pi times 0.1 square divided by 4. And let's see what is the value of V. That is 0.04 divided by pi divided by 0.1 square, 4. That is 5.09 meter per second. Therefore, with this value of velocity, our Reynolds number will be velocity times diameter divided by nu. This is 5.09 times 0.1 divided by 1 times 10 to the power of minus 6. So this gives us the Reynolds number of 5.09 times 0.1 divided by 1 times 10 to the power of minus 6. That will be 50900. This is 509,000. So when we have Reynolds number, we also need to find our relative roughness. Let me write this here, 509,000. And relative roughness is E over D, and E will depend on our material, isn't it? And our material is wrought iron. And to find out what is the roughness for wrought iron, let's go back to our Moody diagram. So in here, our wrought iron is 0.046 millimeter. So let's plug it in here. 0.046 divided by remember that the unit is in millimeter, and for relative roughness, there is no unit. So if 0.046 is in millimeter, the diameter should be in millimeter as well. So this is divided by 100, and this is equal to 0.00046. And with these two values, we certainly can find the friction factor. Now let's go back to our Moody diagram, and let me write it here first in case we forgot. So Reynolds number is 509,000, and our relative roughness is 0.00046. And before that, let me clear this up. Okay, now where is our Reynolds number? That is 509,000. So we are looking here. This is 100,000, 200, 300, 400, 500. 509,000 is close enough to 500,000. So we are just going to follow this line and see where it intersects with our relative roughness. And our relative roughness is 0.00046. So I'm going to follow this line and see where does it intersect with our Reynolds number. So it should be about here. Okay, and if we go to the left, and let's see what is our friction factor. So our friction factor is about, this is 0.015, so 0.016, 0.017, 0.018. So I'm going to say that this is F equal to 0.0175. Does that make sense to you? I hope it does. Okay, so now let's take this value and plug it in our equation. Now we know that our F is equal to 0.0175. And again, please do not worry about the value of F too much, because if you find out to be 0.0173 or 0.0177, it should still be okay. Because remember, you are using the Moody diagram using your own eyes. So it's okay to have some error there. But if it's too much, it's not acceptable. So now I think we have everything to complete this equation. We have F, we have L. Length is now 20 plus 10 plus 20. Because we only need to find F once, because everything is 100 millimeter. So length is going to be 50. Diameter is going to be 100, that is 0.1 meter. And velocity is going to be, I believe we have that, 5.09. And gravity is 9.81. And basically we have everything to calculate for this term. Right? Now, let's focus our effort now into finding what are these values. Okay, first of all, what is K entrance? Okay, K entrance is here when the flow is exiting the tank and into the pipe. And to find K entrance, we need to refer to the table that we've seen before that lists all the Ks. Let's do just that. So this is our table. And let me clear everything for you. Remember, we are looking for the entrance flow. And I believe that entrance flow is here. This is square edge entrance. This is similar with our problem. And the K is 0.5. And conveniently, it is listed under 10 centimeter or 100 millimeter. Of course, when you go to work in industry, it's not going to be as easy as this. But for now, let's just take K equal to 0.5 and go back to our note. So K here is 0.5. What about K of the valve, right? For the valve, is here, okay, and the valve is screwed globe valve fully open. Let's take a look at the table again. So screwed globe valve, it is screwed globe valve fully open, and the diameter of the pipe is 10 centimeter or 100 millimeter. So our K value should be 5.7, and let's write that in our note. So K valve is 5.7. What about K of the elbow? And K of the elbow is here. This is one elbow and this is the second elbow. The value is going to be similar because it's the same elbow. Now, what is that? Let's take a look at the table. Where is the elbow? Elbow should be standard elbow at 10 centimeter. That is 0.64. So if we go back to our note, this will be 0.64 and also 0.64. And what about K exit? Where is it? K exit is here. And this is the exit flow where the flow exit from the pipe and into the tank. Let's take a look at our table. And K exit is pipe exit, which is 1.0. K equal to 1.0. Now let's go back. And K exit is 1.0. So now you have everything that you need. You have K entrance. I'm sorry if this is a little bit messy. You have K entrance, you have K valve 5.7, K elbows 0.64 and K exit is 1.0. Let me show you again. So this is our K entrance, this is our K valve, this is K elbows, and this is K exit. If you have more components, then you will have more Ks. This is why in the previous video, I have told you that it is not necessarily that major loss is greater than minor loss. If a piping system has a lot of fittings but very short, then the minor loss could exceed the major loss. Right now, I think we have everything we need to solve this equation. Now, let's just go and plug in the number. Now, because this is so messy, I'm going to copy everything and put it here. Okay, now we know that we need H. So H is equal to 0.5 plus 5.7 plus 0.64 plus 0.64 plus 1 times velocity square divided by 2g. Velocity is 5.09. This is 5.09 square divided by 2g, 2 times 9.81 plus this term, so plus, what is our F? F is 0.0175, 0.0175, L is 50, D is 0.1, velocity is 5.09 square, and divide by 2 times 9.81. Now, I think this is quite convenient because we already have all the values. So, let's plug it in our calculator. This is 5.09 square divided by 2 divided by 9.81 times 0.5 plus 5.7 plus 0.64 plus 0.64 plus 1. That is 11.197. I'm going to write 11.2. That is our minor loss plus 0.0175 times 50 times 5.09 square divided by 0.1 divided by 2 divided by 9.81. This is 11.55 meter. Now, we know that this is your minor loss and this is your major loss. The total of these two is 11.2 plus 11.55. 22.75 meter. And that is the answer. Okay, now you can see that in this particular problem, the major loss is slightly higher than the minor loss. And the total is 22.75. That is your total loss. And your total losses is similar with H. And we are looking for H. So our H is equal to 22.75 meter. Alright, and that is how you find minor loss together with the major loss. So for me, I think the tricky bit about minor loss is you might miss K. Because there are so many components inside there, you might miss either K entrance or K exit, and that makes your answer wrong. So please be careful and look at the problem very carefully and try to find out as many Ks as possible. And of course, the value of Ks is there inside the table. So as usual, you can do this example again and again and keep repeating this video again and again until you can do it, until you can solve it without even looking. That is all from me for now, and I'll talk to you soon. Bye!